Example 2.2.1a. Compare the total resistance of 35 meters of 20 gauge copper wire to the resistance of 35 meters of 16 gauge copper wire. The cross-sectional area of the 20 gauge wire is 5.2 times 10 to the minus 7 square meters, and the cross-sectional area of the 16 gauge wire is 13 times 10 to the minus 7 square meters. The resistivity of copper at 20 degrees Celsius is approximately 1.72 times 10 to the minus 8 ohm meters. What would be the resistance for the 16 gauge wire if it was composed of aluminum with a resistivity of 2.82 times 10 to the minus 8th ohm meters? So we're going to start like we always do. We're going to go ahead and write down our givens here in the answer. Hopefully you're used to this by now. So the length of both of these segments of wire is 35 meters. We have two different wires, a 16 gauge wire. Its cross-sectional area is 13 times 10 to the minus 7th square meters, and then we have the cross-sectional area of the 20 gauge wire, which was given to us at 5.2 times 10 to the minus 7th square meters. We were given two different resistivities for the materials. Resistivity of aluminum, that's rho sub Al, I guess capital A lowercase l for aluminum, 1.72 times 10 to the minus 8th ohm meters, and then the resistivity for copper Cu is equal to 2.82 times 10 to the minus 8th ohms per, or ohm meters. So there are our givens. We are asked to find the total resistance of the wire if it's made of copper and is 20 gauge. We're asked to find the total resistance of the wire if it's made of copper and it's 16 gauge. And then we were also asked to determine the total resistance of a 16 gauge wire made of aluminum. So I'll call that Al16. So those were the three things that we were asked to find. The solution is that from the equation presented in the text, the total resistance of a device or length of wire or anything is the material property resistivity, rho, in ohm meters, times the length of the section of wire, and then we need to divide that by the cross-sectional area. So what this is saying is that resistance is proportional to length, inversely proportional to cross-sectional area. So for copper, we're pulling down this value of, I wrote these backwards here, I just noticed in the givens. The resistivity of copper is 1.72 times 10 to the minus 8th, and the resistivity of aluminum is 2.82 times 10 to the minus 8th. That should have been obvious. Copper is a better conductor than aluminum and therefore has a lower resistivity. I apologize for that slight mix-up there. Anyway, resistance is going to be the resistivity of the material. So for the resistance of a 20 gauge copper wire, I need to take 1.72 times 10 to the minus 8th ohm meters. And then I need to multiply that by the length, which was 35 meters long, and I need to divide by A, which is the cross-sectional area. If this is a wire, what we're talking about is that surface area right there, the surface area of that circle. So in this example that was given to us as for a 20 gauge wire, it's a relatively small cross-sectional area of 5.2 times 10 to the minus 7th square meters. So we can see that meters times meters is square meters. That's going to cancel out, leaving nothing but ohms, which is the unit of resistance we all know and love. So that gives us a total resistance of that length of wire of 1.2 ohms. So that's RCU20. RCU16 is going to be the same calculation, that 1.72 times 10 to the minus 8th times 35, and we're going to divide that now by the cross-sectional area of that of the 16 gauge wire. The cross-sectional area of 16 gauge wire is 13 times 10 to the minus 7th meters squared. So hopefully you're familiar with the gauge nomenclature of wires. If you're not, I want to point something out real quickly though. The gauge is inversely proportional to cross-sectional area. So here we've got 20 gauge wire. It's got a cross-sectional area of 4.2 times 10 to the minus, or sorry, 5.2 times 10 to the minus 7th. And here we have a gauge of 16, and it's 13 times 10 to the minus 7th. So the smaller the gauge of wire, the bigger the cross-sectional area. So smaller gauged wires are larger wires. 20 gauge wire is a smaller wire diameter-wise than 16 gauge. Anyway, we get an answer there of 0.463 ohms for that calculation. So we also see that as wire diameter increases, the resistance for the same length decreases. So bigger cross-sectional area wires for the same material have a lower resistance associated with them. So now we've compared two wire diameters or cross-sectional areas to one another for the same material. What happens if we now just go ahead and change that material? And so we're going to say the resistance of a aluminum wire that is 16 gauge. What happens if we do that? So that's going to be the resistivity of aluminum, which from the problem statement was 2.82 times 10 to the minus 8th ohm meters. We need to multiply that by 35 meters, which was the length of the wire we're analyzing. And we need to divide that by the cross-sectional area here. Same cross-sectional area as in the previous example because it's the same gauge. So 13 times 10 to the minus 7th square meters, and we get 0.759 ohms. So we see that because copper has a lower resistivity, it also has a total overall lower resistance for the same length wire. So we have our calculations. The answers are in ohms.